My final project, which is about chaos and the Lorenz Attractor. This is from chapter 9 of the Strogatz textbook, and I'll be doing my best to really unpack what this all really means about chaos and these things called the strange attractor. So to break down this presentation, I'm going to first be going over some brief background of what chaos is, and then unpacking this system known as the Lorenz System by looking at simple properties of it and tying it with bifurcation that's happening at certain places, and then looking at what it means for an attractor to be strange and looking at the chaotic behavior on it, and ending with the Lyapunov Exponent, which has some relation to chaos and what Lorenz was looking at in his basically his studies of weather prediction. So the main objectives that I really want to cover is to have a basic, for you guys and also myself, to have a understanding of what the Lorenz system is and the Lorenz attractor with some chaos context to it, and then connecting the Lorenz system to bifurcation, as well as really unpacking the meaning of what makes an attractor a strange attractor. So some historical context that I think is actually important to go over first is that we're looking at some mathematician named Edward Norton Lorenz, and he was an atmospheric scientist who really recognized chaos theory with his studies of weather forecast predictions. And he did publish this one paper of his results titled Deterministic Non-Periodic Flow from 1963. And I actually did some reading of it. Some of its sections of the paper actually ties into what I'm going to be presenting, and it's really all about his studies of the atmospheric convection rules and how during his time he was able to really construct this 3D system that represents some chaos behavior basically with the atmosphere. And he really discovered that trajectories in 3 dimensions can actually have really a significant change to them on its outcomes based on small tweaks to its initial conditions. And really it's like saying that like small changes can lead to greater or like significant outcomes, which is like tying to this quote that he says about when a butterfly flutters its wings in one part of the world, it can eventually cause a hurricane in another. So it's really how like a small action of, like if you think about like a butterfly flapping its wings, it will cause in the long run a large disrupt of maybe some chaos in another location of the world. And he was known for coming up with this 3-dimensional system, which was named after him, the Lorenz System. So to first looking at what is chaotic behavior, there's no official definition of it, but there are some certain criteria of what makes something chaotic. And one thing is that there is aperiodic / or non-repeated like behaviors over time. So like the motion is something that's non-repeating. There's also deterministic, which means there's some irregularities for a system coming from its nonlinearity terms. And also the outcomes of a system is sensitive from changes of initial conditions. And that's really saying we're looking at 2 trajectories, but with one trajectory having a very slight change to its initial condition from the other trajectory, you'll see that there's actually, in the long run, there's going to be some really significant difference of their outcomes when you're comparing both trajectories. And really, there's chaos theory to this. So some examples of it would be road traffic, heartbeat irregularities, and weather forecasting, where there's a lot of, some randomness or like unpredictableness to it, where there's nothing like really like constant going on. So that's part of like chaos. So I think to really understand this and to have a good visual of what chaos is, it's looking at this model known as the chaotic water wheel. And this system is really showing a motion of a water wheel where water is being poured from the top, like a spout, into these buckets on the water wheel. And eventually you'll see that the water wheel will be rotating at different orientation from clockwise or counterclockwise, and also its speed of rotation changing, more like in a random state. So like there'll be some unpredictableness to it. I think to really get a better understanding, it's good to watch a video of this. So we have this system, this water wheel, and we see the spouts on the top. So first it's motionless, but then once water starts pouring, you see that some water will be contained in this first bucket, and then its weight will cause the water wheel to go counterclockwise. And you'll see that the speed is changing. Sometimes it's going slow and then really fast. But then eventually, when all the buckets are filled, the water wheel will be changing orientation, so it'll be going clockwise and then counterclockwise and vice versa. But yeah, so the main idea about that is that the rotation is, as water is filling up the buckets, the rotation is becoming destabilized. So there's like chaotic motion to it. And we really see that the wheel changes directions over time, it slows down, etc. So that's really what chaos is really like the illustration of chaos. So the Lorentz equations, Lorenz was able to simplify some complicated, these complicated equations from when studying the atmospheric convection rules to this x dot equals sigma times y minus x, y dot is rx minus y minus xc, and z dot equals xy minus bc. And we see that in this system we have three parameters, and they're often fixed values, but sigma is known as the Prandtl number, r is the Rayleigh number, and b doesn't have a name. But common values that Lorenz was working with on these parameters was that the Prandtl number would be equal to 10, b equals to 8/3, and r equals 28, while x was the rate of convection flow, y was temperature difference between ascending and descending currents, and z was vertical temperature distribution. So what this all means was that this system was really modeling where if we have basically heat from the bottom of a cup, then the heat and like steam will travel up, but when it reaches to the top of the cup, it cools down and it will cause the heat to travel back down, and it will be this cycle of where heat is traveling up and down and cooling off. So that's what really is like a simplified version of what Lorenz was studying in the atmosphere. So to really unpack the Lorentz equations, there are some simple properties of it. We have that there's symmetry to it. So if we were to negate x dot, y dot, z dot, it would also be the same. So there's invariant to it. So if x, y, and z is a solution, and so is the negation of that negative of it. So negative x, negative y, comma negative z is also a solution. We also will see that volume contracts over time and phase space, so the system is dissipative. The origin is a fixed point for all values of the parameters from the Lorentz equation. And there's some symmetric pairs of some two other fixed points that we'll be looking into, denoted C plus and C minus, and also that the origin is globally stable for r less than 1. So to first look at the volume contraction and why the Lorentz system is dissipative. Basically, volume in phase space, in 3D phase space, is that we wanted to look at how volume evolves over time. And so if we have some arbitrary 3D volume here, this 3D shape, and we're really curious to look when its transformation into some other arbitrary shape where it's volume at time plus delta t, so there's a time difference between these two. And we want to see, really, we want to find, understand how does volume evolve. So to really look at this is when we begin looking at the volume, we have the volume, but the way to numerically look at it is that if we look at patches on the surface of this volume shape, and we basically sum up all the patches, we will find that if we sum them up plus the original volume, and we integrate all these patches on the surface, we're able to find the volume basically at what the volume really represents. So the volume at t plus delta t is really the original volume plus this new surface with the patches, by adding up the volume of these tiny patches on the surfaces. And really we're really tying in some vector calculus over here, where we basically take the partials of the Lorenz system, and after doing all this computation, it turns out that v dot is just negative of sigma plus 1 plus b times v, which turns out to be just a one dimension ODE with some constant coefficient that's negative. And volumes in phase space actually shrink exponentially fast, so at some time t. So really it's saying that if we have some trajectories starting anywhere, it will eventually tend to a limiting set of zero volume. And that's really saying that what we're going to see later is that trajectories will end up to some fixed points or limit cycles, or something known as the strange attractor. So next to look is the origin and its stability. And over here, if we study the Lorentz equation, you can see that when we set x dot, y dot, z dot all equal to 0, you will see it's quite easy to see that x, y, and z all being 0 will actually satisfy that. And to evaluate, basically to check its stability, we could take the Jacobian of it, where the entries of the Jacobian are all the partial derivatives of x dot, y dot, z dot, and evaluate it at the origin. So the Jacobian turns out to be this 3x3 matrix over here, and when we evaluate it while taking the standard parameters values of sigma equals 10 and b equals 8/3, we see that it turns out to be this matrix. So after doing all of that, I was able to find the 3 different eigenvalues. There's a lot of computation to it, but it turns out to be that we have 1, it's we have lambda 1 is some negative real eigenvalue, and then lambda 2 and lambda 3 are the same except with a negative and a positive radical 81 plus 40r. And when we're looking at different values or different cases of r, we see that when r is less than 1, all eigenvalues are negative, and that indicates a stable node. However, when r is greater than 1, lambda 1, lambda 2 are negative, while lambda 3 is positive, and that turns out to be some saddle point, which is unstable. So below we see the different diagrams, and just saying that for stable, we have that in all three directions, its trajectories are approaching this fixed point, the origin, which is stable. While for saddle, in two directions, it's attracting, but in the third direction, it's going away, so it's repelling. And another interesting about the origin is that it's actually globally stable for r less than 1. So what that really means is that for r less than 1, all trajectories are approaching that all trajectories that start near the origin do approach the origin as time goes to infinity. So it's heading towards the origin. And basically to do this is that what Strogatz also says is that we can really see this by constructing a Lyapunov function. And through this method, it's finding a way how basically if we're able to satisfy these conditions of what's known as a Lyapunov function, we can see that there's a generalization that all trajectories will head towards our fixed point 0. So there's two properties for a Lyapunov function. It's that v of x, y, and z are greater than 0 for all x not equaling the fixed point, and v of x star, y star, z star is equal to 0, so v is positive definite. And that v dot, when we take the derivative, it's less than 0 for all values of x, y, and z not equaling the origin 0, 0, 0. So we can construct a Lyapunov function where it was given as 1 over sigma times x squared plus y squared plus z squared. And we can take the derivative of that, and that turns out to be, after doing all that work, we get negative x minus r plus 1 over 2y quantity squared minus 1 minus r plus 1 over 2 squared quantity times y squared minus b z squared. And we see that really that for all values where it's not equal to the origin, so when x, y, and z are not 0, we see that all the terms are actually going to be, when we sum them up, it's a negative sum of squares, so they're actually less than 0 the whole time. So there's a really it's always negative. And the only time that v dot is 0 is really when we plug in x, y, and z are all 0. So v dot is only 0 at the origin. And it really just shows that basically the origin is globally stable, and that's really the criteria of that, what it means that all trajectories for r less than 1, that the trajectories will approach the origin. So we uncovered the origin and stability, and the next step would be to look at the other two fixed points that we find. So basically, the other two fixed points was found the same way, where we set x dot, y dot, z dot equal to 0, but we let z equals r minus 1. And after doing some math, it turns out to be that x star and y star are both equal to plus or minus square root of b times r minus 1. And Lorenz called these two fixed points C plus and C minus. So here, this is C plus, where the radical terms are positive, and then C minus would be the same thing as this fixed point, but with negative radical. But over here, we're going to be just first looking at C plus. So basically, the Jacobian matrix evaluated at this fixed point. And we get this 3x3 matrix, and we can obtain the characteristic polynomial. And there is a shortcut to finding that, where we just have lambda 3 minus the trace of this matrix times lambda squared plus the sum of minors along the main diagonal minus its determinant, the matrix, setting equal to 0. And after doing all that computation, it turns out the characteristic polynomial is this, so lambda cubed plus sigma plus b plus 1 times lambda squared plus r plus sigma times b lambda plus 2b sigma times r minus 1 equals 0. And this characteristic polynomial is just a case if we were to plug in those standard parameter values where sigma was 10 and b was 8/3. So after doing all the computation, it came out to be that we still get 3 eigenvalues, where lambda 1, lambda 2 are just different signs of each other, of the imaginary I times the square root of b sigma plus r, and then lambda 3 is negative sigma plus b plus 1. And really, we wanted to see that there's actually some sort of value r where there's basically a Hopf bifurcation that occurs. And really, it's to show like where C plus and C minus are basically stable. And really, this is part of also a supplementary exercise from the Strogatz textbook, where we want to look at C plus and C minus and really look at the stability of it as well, and show at where this Hopf bifurcation is happening. So we seek the solutions of the form lambda equals I times omega, where omega is real, and show that there's a pair of pure imaginary eigenvalues when this R value is the Hopf bifurcation value of really sigma times sigma plus b plus 3 all over sigma minus b minus 1. So I'm basically the pair of pure imaginary eigenvalues will be important later on. But over here, this is just some of the computational work of how to show that basically, we get a Hopf bifurcation value of r sub h. And we're just letting lambda equal I times omega and plugging that into our characteristic polynomial. And we do see that this value r is going to be positive. So as I mentioned before, we obtain 3 eigenvalues, and after doing all the work, we see that there's a pair of complex eigenvalues, and to find the third eigenvalue, we use something known as Vieta's formula, and that's just some sort of way of finding some interesting properties of some roots to polynomials. And we see that there's a negative real eigenvalue, which would be lambda 3, while lambda 1, lambda 2 are 2 complex eigenvalues. And it's stable for when r is greater than 1 and less than this r sub h, basically the Hopf bifurcation. And at r equals 1, there's actually a pitchfork bifurcation. where basically these two, the stability of these two fixed points, C plus and C minus, would merge together at the origin when r equals 1. And the same results would be attained for C minus as well. But this was just showing you how the process of looking at the different eigenvalues for our fixed points C plus. So basically C plus and C minus turned out to be stable. And we're looking at 3 dimensions, so there's some new things going on where in 3 dimensions, when there's stable fixed points, they are surrounded by saddle cycles. And this is with the subcritical Hopf bifurcation. So we have a fixed point here, but we have a limit cycle as well. But we see that trajectories are heading away from the limit cycle, so it's unstable. And that's what makes a saddle cycle. And if we were to look at all the trajectories and the stability of it, this graph really sums up of what we found so far. So as I mentioned earlier, at r equals 1, there is some pitchfork bifurcation. And so the origin is stable for r less than 1 over here, and then we also have stability for C plus and C minus. But the interesting part is when r equals r sub h, there's this Hopf bifurcation where there's going to be these unstable limit cycles, unstable cycles happening, and we see that there's some sort of interesting things going on where C plus and C minus are stable, but then they're going to lose stability once it reaches r sub h and afterwards. And it turns out to be that basically it loses stability, and actually that basically the fixed points absorbs the saddle cycles, and it just changes its stability. But the main thing that we're looking on for chaos and strange attractor is really what's happening in this region when r is greater than r sub h. And this is where we're going to see some new things going on with some chaotic behavior and strange attractors. So right now this is just a summary of what we found so far, basically for the origin and for those 2 fixed points C plus and C minus. So we get stable and globally stable for r less than 1 for the origin, while it's unstable for r greater than 1. And for those C plus and C minus fixed points, it's stable when r is between 1 and r sub h, and it's unstable for r being greater than the Hopf bifurcation value. So as I really mentioned before, we're interested what happens when r is greater than r sub h. And that's when strange attractors appear. So we found that before r sub h was sigma times sigma plus b plus 3 divided by quantity of sigma minus b minus 1. And when Lorenz plugged in his parameter values for sigma and b, it turned out to be that the value for Hopf bifurcation was around 24.74. So that was like the boundary, or the value that when r was greater than that value, there would be those fixed points of C plus and C minus would become unstable. And he also discovered that beyond that, after in that region where r is greater than 24.74, that trajectories were actually confined in a bounded set of zero volume, which we did uncover before, of how the system is dissipative. So trajectories are confined in a bounded set, and that trajectories do not intersect themselves. And we'll see the case where they don't intersect themselves later on in this presentation. So to go over the strange attractor, it's first important to know what a attractor is, and really what it is that it's a set where all neighboring trajectories converge. So we see that stable limit cycles and stable fixed points are actually examples of an attractor, because trajectories over here, they head towards the limit cycle, and over here for the fixed point, it's heading inwards, heading towards the origin in this case. But for a strange attractor, it's really a region in phase space where trajectories are acting differently, and trajectories are making like wild jumps and skips around, with where this chaotic behavior happens when you actually change their initial conditions slightly. And we're going to see that so trajectories are bounded to a set of zero volume, and that later on when Lorenz basically does some numerical computation on his system, we'll find this different shape that's known as the Lorenz Attractor, which will be classified as a strange attractor. So chaos in the strange attractor. So Lorenz was looking at the trajectories and how it would behave in the long run of time t. And we see that over here, he picked an initial condition with 0, 1, 0. And he basically simulated this and just let it ran for a long time. And in the end, he noticed these strange things happening. So we can see that the motion, there's a lot of irregular oscillations happening, where it's first jumping up positive and then going all the way down negative and oscillating more and more. But then in this part, we see like the motion's aperiodic, where it's making craziness and a lot of chaos going on, because there's no repeated patterns, just to put simply. And this actually goes in line with the chaotic water wheel, because if you were to think about it, the chaotic water wheel was rotating perhaps counterclockwise at first, but then it suddenly changed to the clockwise direction, and also its speed was changing as well. And we really see that the water wheel had similar behavior to this, and it turned out that if you did like some sort of change of variables for the Lorentz equation, you would get the water wheel system. So this is just another view of the Lorenz attractor, but this is for basically when you're looking at the viewpoint of basically when he plots x of t against z of t. And this is really where you get to see this butterfly shape of the trajectories. So we see that if a trajectory were to start very close to the origin, it goes away from the origin, so the origin's unstable here. And then it will curve and loop around here on the left side. And then eventually it will cross over, loop around, getting wider and wider, and then go back to the left side, and it keeps happening. So we actually have the origins unstable, and then over here, these two regions, these 2 points, they're also unstable fixed points. So we really see that there's a lot of basically strangeness happening over here, and that there's a lot of unpredictable from basically one cycle to the next cycle over time. So this is what really caught the attention of what made something a strange attractor and how its behavior differed a lot compared to what we previously looked at in terms of like just stable fixed points and stable limit cycles. So to really look at with chaos, it's something known as the Lyapunov Exponent and how it's related to what we mentioned earlier about chaos. There's sensitive dependence on initial conditions. So really it's like if we were to look at two trajectories starting close together at some distance delta naught, we'll see eventually the two trajectories will diverge from each other. And I think it's better if I were to draw a simple diagram of this. So let's say we have one trajectory over here, and it goes this way. So this would be, let's call it x of t. And then in another color, another trajectory starts very close to it, but there is a small distance, and it goes this way. And if the distance between these two trajectories at starting point where t is equal to 0, we call this small distance delta naught. And basically what's happening is that, so this is x of t plus delta t. And we see that the distance between these two trajectories will diverge from each other, and it's exponentially. So this is basically there's some exponential growth, and really it's that at delta t. So what I mean by exponential growth, it's that it comes down to be that delta t is equal to, when we look at exponential growth, we know there's some constant, delta naught times e to the lambda t. And lambda is actually known as the Lyapunov exponent. So what that really means is that delta really grows over time, and the distance between x of t and x of t plus delta t is, their distance between them increases. So going back, there's exponential growth of the distance between these two trajectories, and the Lyapunov exponent, when it's positive, and that really indicates chaotic behavior, and that's just some sort of property of it. So the textbook also goes into some detail of looking at what the Lyapunov exponent value is. And if you were to graph the natural log of delta of this magnitude with t, and we first get this basically this trajectory where it's, like oscillating. But if you were to really like take the slope of it and round it, it turns out to be that what Lorenz discovered is that the Lyapunov exponent was 0.9, and that's positive. And what this all really meant for him was that he was using this for weather prediction. So if you were to predict the weather, let's say like 15 days from the present day, you start at time 0, and you can predict the weather, but there will be some basically some time, and where there's going to be a tolerance where your prediction of whether maybe it's going to be rainy or sunny at day 14, it's actually not going to align to what the real weather will be. So your prediction is going to fail at some t sub horizon. And basically it's saying that he used this Lyapunov exponent to help calculate when this t sub horizon would be. But I didn't really have much time and understanding of how this exactly works, but the main idea was that he used the Lyapunov exponent and its value to help make certain predictions of when his prediction will be in line, and then when it will actually fall out and become basically a different outcome. So when we're really looking at how there's a lot of sensitivity to the initial conditions of trajectories. And if we were to look at two trajectories, for instance, we see that both have a very, very similar initial conditions, where for the x, it's just differing by 0.001. And we see that in the beginning, both trajectories do start off the same manner. But then at some time, I guess time around 22 seconds, or even maybe a little bit below that, the two trajectories will actually exert different outcomes. So that's why I meant before when I said that there's initial conditions of when you tweak them, it's going to actually have a significant outcome to it. And we see that for the rest of time, the trajectories are completely different, and it's all chaotic over here. So I think to really wrap this up is to look at the Lorenz Attractor in 3D phase space and to see really what's happening to the trajectory as time goes to infinity. So there's a MATLAB code where there's a function, the Lorenz System, and we basically set our parameters fixed, and I just chose some arbitrary initial condition. And it's really gonna show a 3D simulation or animation of what's happening to the trajectory over time. So if we were to run this, we see it first starts at its initial condition, 10, 8, 10. And it's gonna be spiraling, just like how people called it. It looks like a pair of butterfly wings. So we see that it's going to spiral on the left side, and then eventually cross over to the right side and spiral some more, and then comes back to the left side, spirals again, and eventually cross back to the right side. And this whole shape is really a strange attractor, but it's named the Lorenz Attractor, where the Lorenz Attractor is a type of strange attractor. So I think this was pretty cool just to see visually what it means for some attractor to be strange and the behavior of it. And I think the geometric structure of it's pretty interesting. So we can see there's a lot of different motion to it over time. And to really conclude, it's about the strange attractor and chaos. It's that as time goes on, trajectories are still bounded in some region or phase space, but as we see from the butterfly, the trajectories are actually, it looks like they're merging together, but they're actually not intersecting themselves. And through this work, Lorenz was able to argue and conclude that for some long-range weather prediction, you can't really make an accurate, guess of what the weather will be like 15 days from now, because there can be very small changes where it's going to actually lead to a different outcome of the weather. And yeah, we did see that some parts where for two trajectories that are starting very close or having very similar initial conditions, they will actually have a completely different outcome to it. And I hope you guys had a better understanding of what chaos and a strange attractor really means, and thank you for your time. And these are some references of just where I got some of my information from and sources.